Good afternoon, everyone. My name is Francesco Petruccione. I'm the interim director of NITheCS, and I have again the pleasure to introduce the speakers of this April mini-school. Yeah, and today's speaker is Dr. Anke Kallau, straight from Germany. And I will ask Professor Bruce Watson, that you had already the opportunity to meet the last 2 weeks, to briefly introduce Anke. Yeah, Bruce, please.
Good afternoon. Thank you, Francesco, for hosting this mini school through NITheCS. Our speaker today is Anke, and I'll try and pronounce her surname correctly, Kallau, from TU Dresden. This follows on our series on respaces, vector lattices, and ordered structures. And Anke will be talking about positive operators. So far in the mini school, we've looked at the spaces, we've looked at the order structure, we've looked at the lattice structures, we've looked a little bit at order continuity, convergence, but today Anke will take us into the domain of operators on these spaces. Thank you, Anke. Would you like to proceed?
Of course. Thank you, Bruce, for the introduction. So this is the third lecture in 4 lectures mini course of Bruce Watson. So we agreed that today I take you to a little journey into the world of positive operators. The purpose of this is that Bruce in the next lecture can apply all the things I will tell you today to very interesting topics in stochastics and other fields. So Bruce will do the applications next week, and this week I give you the basics on positive operators and different classes of positive operators that will be needed in the applications later. So this is the plan for today. Before I start to introduce positive operators, I would like to quickly recall what Bruce already told you about ordered vector spaces and a bit on vector lattices, but it's just a quick repetition of the things you have already heard. So what is our setting? Our setting is a vector space equipped with a partial order, and this partial order should be compatible with the vector space operations. So it should be compatible with the addition, and it should be compatible with the scalar multiplication in the way that is written in A and B. So if you add an element, it should not disturb your partial order. And if you multiply with positive numbers, if you multiply a positive element with positive numbers, then the partial order is kept. And all standard sequence spaces or function spaces you can equip with the pointwise order, and these orders satisfy this, so they are compatible with the underlying vector space structure. So the set of all elements that are greater or equal the 0 element of the vector space gives then a cone, meaning that I can add 2 positive elements, or I can multiply them with positive numbers and I stay in this cone. And second, if I intersect the cone with minus the cone, then I only have 0. So all elements of the cones are called positive, and this setup will be our basic one. These spaces we call ordered vector spaces, and denoted by x or k, x and k, or abbreviated by x. So, and the concept of these ordered vector spaces and the concept of cones, this is one-to-one. It doesn't matter whether you start with a vector space order and then take the set of all positive elements, or whether you start with a cone with these properties. Then you can introduce a partial order by x less equal y if and only if the difference is in the cone. So these concepts are one-to-one. Good. And then you observe, so these cones, for example, take this 4-ray cone, yeah? that you put in the, so you have a cone with 4 rays starting in 0. And then you can look at upper bounds of elements. Here I was drawing 3 elements for you, u, x, and y. And it depends how the elements are in the space. Some of them, when you intersect the set of upper bounds, then you get the same shape of the cone. So that means that this shape, it's here on the right side, has a smallest element. That means the supremum exists for the 2 elements x and y. On the other hand, for such a cone, if you choose 2 other elements where the sets of upper bounds, when you intersect them, have a different shape, so like a wedge, as in the left, on the left side, the left gray area here, then this intersection doesn't have a smallest element, so the supremum does not exist. So it is very special that for all elements, the supremum and the infimum exists, and this will lead us to the concept of vector lattices that Bruce already discussed with you. So what we want is, in many cases at least, that X is in addition a vector lattice or a Riemann space, meaning it is an ordered vector space such that for every any 2 elements, we have that the supremum exists. And due to the vector space structure, it's then easy to show that the infimum exists as well. And these vector lattices are nice in a way that you can do many calculations as in you can do with the numbers, because you can define for an element x the so-called positive part. So this is the supremum of x and 0. Yeah, you call it x plus. When you have, for example, functions in mind, you take the pointwise supremum of the function and the 0 function, and this is then the positive part of f, as is done many instances in the analysis. You have the negative part, which is the supremum of minus x and 0, and you have the modulus as the supremum of x and minus x, yeah, which is this element above here. As long as it, if it exists in the vector, if it exists, you have these 3 nice objects. So, but please be aware of the fact that these lattice codes are something very special in the big set of all ordered vector spaces. So there are many ordered vector spaces. Here on this slide, I'm drawing all the cones or different cones that are possible, from the 3-ray cone, the 4-ray cone, till the so-called ice cream cone, circular cone, and in between different polyhedral cones. Here I'm only now 3, of course. And among all these many cones, only the 3-ray cone is a lattice. All other cones lead to partially ordered vector spaces. So you see that the vector lattice case is something very, very special. And this is it's an old result, yeah. When you are in Rn, then you need n extreme rays of the cone to obtain a lattice. If you have more extreme rays, you are out of the lattice theory, but you are still in the theory of ordered vector spaces. So now let's come to operators. So assume we have 2 of these ordered vector spaces, x with a cone x plus and y with a cone y plus. And we deal with linear operators from x to y. And operator is called positive if for every element in the cone, the image is in the cone as well. So for x greater or equal 0, we obtain the tx is greater or equal 0. In other words, T maps the cone x plus into the cone y plus. These operators we call positive. And these operators appear everywhere in analysis. And I list some examples for you. I start with 2 very simple examples. So the first example, we look in the space of continuous functions. And when I take a pointwise positive function, then it's clear that the integral is also a positive number. So here we have a positive operator or positive functional. And C of 0, 1, this is a vector lattice, of course. No, here the supremum and pointwise infimum supremum exist. But of course, you can do the same for subspaces of the space. Say the 1 times the continuously differentiable functions, which is still an ordered vector space, but not a lattice anymore. Yeah. So please be aware of the fact that subspaces of vector lattices, they inherit the order, so they are still ordered vector spaces. But in general, they are not vector lattices anymore. So you taking subspaces, you are out of the lattice theory. But anyway, these positive operators are defined on ordered spaces, so you can define it there as well. So this is a very simple example of a positive operator. Then the second example, we consider matrices. So in linear algebra, you look at maps from a space Rn to Rm with, and both spaces are equipped with the standard pointwise order. And a matrix gives you a linear map from X to Ax. And it is a straightforward calculation that this is a positive map in a sense above, if and only if all entries are positive. If you take other cones in Rn and Rm, not the standard pointwise order, but more general cones, as in the pictures above, then always the question arises, okay, which matrices are the positive operators with respect to these more general cones? Yeah, this is not as clear as in this easy case. So the pointwise positive matrices belong to the standard order in the underlying spaces. So, and then in other situations that Bruce will need in his last lecture, positive operators appear in different settings. In number 3 here, in example 3, in LP spaces, if you multiply an element by a characteristic function, this is this positive map and a positive operator, and it's even more, it's a so-called band projection. This is just to list all the things that Bruce will need later on, yeah? Example number 4, conditional expectation operators. These are also positive operators. These are positive projections that are in addition order continuous and have some more additional properties. So they are also examples of our setting here. And number 5, if you start with measure preserving systems and look at the corresponding Koopman operator, these are also positive operators, but they are even more. They are isomorphisms and they are order continuous. So these are many new notions here. And the plan for this mini lecture is to go through all these types of operators, so band projections, order continuous operators, and isomorphisms, that and give you all the theoretical background for these types of positive operators, for these classes of positive operators that Bruce can build on this in the last lecture. Okay, before I go through these classes of operators, I would like to discuss a bit the set of all these positive operators. So we go now one step up. We take the set of all linear operators from X to Y. Of course, there we have a natural vector space structure. We can add operators and we can multiply with numbers. And then we can look at a set of all positive operators and can check which properties we have here. And it turns out, if we add 2 of them, we stay in the set. No? The sum of 2 positive ones is positive. And if you multiply with a positive number, it stays there. So part of the cone definition is fulfilled, but not everything. what is missing is that the intersection of the L plus with minus the L plus is 0. Yeah. This in general is not true, but under very mild assumption, we get this property. And the mild assumption is the following: X, the domain, yeah, the space here, should be a directed space, meaning that for two elements, you always have an upper bound. Or equivalently, this is if and only if the cone is generating, meaning that the cone minus the cone, or the span of the cone, how you would like to say, gives already the full space. So meaning the cone is big enough. And in vector lattices, this is always true because you can always split the element in the x plus, in element x in the x plus part and the x minus part. Yeah, so there you always have this. Every vector lattice is generated, but in ordered spaces you have to add this condition, but it's a mild condition. And if x is directed, then we obtain all properties of a cone. So the set of all positive operators is indeed a cone in the vector space L, x, y. So we have, if you look at all operators here, we have again an ordered vector space. But even if you start with lattices x and y, the space, this ordered vector space, is not a lattice in general. Only in very specific cases, and if you have time, we can discuss this later. In general, it's only an ordered vector space. So even if you start with the theory of lattices and look at operators from lattices to lattices, you end up in the setting of ordered vector spaces, and you are out of the setting of lattices. Maybe some more properties of this ordered vector space of operators. Let me recall the property of being Archimedean. Bruce already introduced this in one of the last lectures. I prefer this definition. So for any two elements where nx less equal y for all n, we have that n is negative. So then if this is true, then y is called Archimedean. So, and if the range space of our operators is Archimedean, then it turns out that the ordered vector space of operators is Archimedean as well. If we want to make it directed, yeah, we have to cheat a bit. We just generate the smallest space out of the cone. So we take cone minus cone and give it a new name. These are the regular operators, LR. So summing up, if the x is directed and the range space is Archimedean, then this object is an Archimedean directed ordered vector space. Yeah? Because directed is because we use LR instead of all linear operators. So make it directed. Why did I tell you all this? Because I want to make clear what it means if I write for an operator s less equal t. Yeah, then I mean it's within this partial order, within the partial order of positive operators. So if I write for operators s less equal t, that means that t minus s is in the cone, is a positive operator. Yeah. So from now on, I can put these inequality signs in between operator, and it's clear in which space I mean it, for which cone, namely for the cone of positive operator. Okay. And this will be used then for the band projections, but before we come there, I want to briefly take you again through the basic notions in vector lattices and in ordered spaces. So Bruce introduced in vector lattices what it means to be disjoint for two elements. So if you have in mind a space of functions, then it is clear what disjoint should mean. Namely, in every entry, one of the two is 0, right? So in function spaces or in sequence spaces, you have an intuition what disjoint means, and you can give a definition in lattices in the way that the infimum of the moduli is 0. And it is straightforward to show that this is the same as the modulus of x plus y is equals the modulus of x minus 1. A simple calculation. And if we want to translate notions from vector lattices to ordered spaces, I just want to mention this trick here once. In lattices, you have the modulus, yeah? You have the supremum of an element and minus the element. If you don't have the supremum, you just replace the supremum by the set of upper bounds. If I write here U, it means the set of upper bounds of these two elements, of x plus y and minus x plus y. So I can replace such an equation like here by just equality of sets of upper bound. That's it. So this is a typical trick to introduce different notions in ordered spaces. And I already gave you the motivation why we want this, because in the spaces of operators, we don't have lattice structure, so we have to introduce other notions in this way. Good. So I have disjointness as in ordered vector spaces, and in vector lattices is the standard one. So we have disjoint complements then, if I have a notion of disjointness, and we can define solidness with the same trick. We can define ideals, which are solid subspaces. And Bruce introduced bands as order-closed ideals. But here I would like to give you a bit of a geometric intuition, because in Archimedean vector lattices, order-closed ideals have the property that they coincide with their double disjoint complement. Yeah, the bands, so the order-closed ideals coincide with the double disjoint complements in Archimedean vector lattices. And in ordered spaces, so we decided to call it a band if it coincides with the double disjoint complement. And this is something that has a, yeah, but one can, in examples, one has a geometric idea of what it means. Yeah, for a set of functions, you take this joint complement pointwise of the set of function and then do double disjoint complement, and you can really see whether this is satisfied or not. So you don't have to deal with order convergence, which is sometimes a bit technical. Okay. In lattices, in Archimedean vector lattices, so order closed, it is the same as a band. In ordered spaces, the notions differ. But this, I don't want to say more about this now. In vector lattices, every ideal is automatically directed. So I put on the ideal the cone, which I get by the intersection of the ideal with the original cone. And this is always a directed set in lattices. In ordered vector spaces, this need not be, just as a RAG. So now let's come to band projections. Now we record what bands are, we can go to band projections. And there are two descriptions of this. And it was well known that in lattices, they are the same. In ordered spaces, it was not so clear in the beginning. But at the end, it turned out they are the same as well. So let's start. An operator P from x to x is called an order projection. So it's if it is a projection and it is positive and less equal the identity. So these are those projections that are in the order interval from 0 to identity in the space of operators equipped with the cone of positive operators. So here I need the inequality of operators, yeah, to describe order projections. And on the other hand, the projection is called a band projection if the range and the kernel are bands. And in this case, the range of a band projection is called a projection band. So for lattices, it was known that these are the same concepts. for ordered spaces was shown recently by Jochen Glück, that they are in fact the same. So every order projection, so every projection between 0 and identity is in fact a band projection. And in this case, I can split a space into a band, in the direct sum of a band and its disjoint complement, and P projects onto B. And the second thing Jochen showed is that every projection band is directed. Good. Okay, so we have obtained the first notion of our list. This was example 3. So the second issue is order continuity, because in example 3 and 4, we needed order continuous operators. Let me quickly remind you what order convergence was. There are different options of order convergence. Let's start with the classical one. So the convergence here is always for nets. Nets were introduced by Bruce last time. So the index set here is a directed set. It need not be the natural numbers. And so a net is indexed by such a directed set. So classically in the literature, you find, in the old books, you find the first type of order convergence. So they say, okay, this net order converges to X if you can, the difference of X alpha and X dominate by another net. And you want to do it, you can put here the modulus if you are in a lattice. If you're not in a lattice, you have to put here plus minus, yeah. But in lattice, it reduces to the modulus. You want to dominate this difference by a net, Y alpha. This should decrease, so the error means decreasing. And this notion meant that the infimum should be 0. So here it means it's a decreasing net and the infimum 0. And yeah, for every alpha, you have this, you can make the difference small between X alpha and X, yeah, by this net Y alpha. So classically, this was used. And then it was observed by Sirotkin and Abramovich. 2000, paper of 2005, they said, okay, but we can construct examples where the convergent, so a convergence should only depend on the tail and not on the whole net. Yeah, only the tail of the net should be relevant for the convergence. And they gave examples that with this order convergence, this is not true. So this here one runs into trouble. And they suggested to give more freedom to avoid this problem, that convergence only depends on the tail. And introduced the second one, O2. So they say, okay, this dominance with the other net, it is enough. It is from a certain element of the index set on. Yeah. Here I look at all alpha that are bigger, greater, equal alpha 0. And only for them, we need this dominance thing here, yeah? So we go, it's enough to have a net from a certain alpha 0 on. And then they avoid the problem they had before. And in the old literature, in the old Russian literature, there was another convergence given by different authors, Wulich, for example. It's called here O3 convergence. And they said, let's even give more freedom. Here the index set doesn't matter of the Y alpha. The rest is the same. Yeah, it should be decreasing net to 0. But they said, okay, for every beta in J of the index set of this second net, there should be an alpha 0 such that we have this this property, yeah, for every alpha from this alpha 0 on. So there were different concepts. And they are related. So from O convergence, we get O2, and from O2, we get O3. Order continuity is then clear. It means continuity with respect to one of these order convergences. So we have O continuity and O2 and O3 continuity. now two continuous, I only wrote it for two continuous here. Every net that O2 converges to 0, then the net of the images should do the same. Yeah. And it's enough to do it for 0 because they are linear operators. And in this paper, Abramowitz and Sirotkin showed that in Archimedean vector lattices, O2 continuous, and for positive operators, of course, T positive, O2 continuous is the same as O3 continuous. So you can choose what you want to take. So it's enough to take O2, the simpler one. And a bit later, with a student, we found out that this does not depend on the lattices. We can do it for ordered vector spaces and obtain the same result. And it is even enough to consider nets that decrease to 0. Yeah, because we have positive operators here. Yeah, we need not even the convergence to 0. It's enough to look at these nets that decrease to 0. So, okay, so far to the order continuous operators. Then we have done example 4. Yeah, there the conditional expectation operators, there were order continuous operators that were positive projections with some more properties that Bruce will discuss with you. So we come to example 5, the Kottmann operator, which is a Riesz homomorphism. What is a Riesz homomorphism? It is a linear operator that preserves the lattice structure. So it doesn't matter whether you first take the supremum of 2 elements and then apply the operator or do the other way around. So these are the operators that fit to all structures that we have in a vector lattice. And there is a second notion, the complete Riesz homomorphisms. They are defined as follows. This notion is defined for sets, subsets of X. If the infimum of A is 0, then the same holds for the images. Yeah, the set of set T of A. And of course, every complete Riesz homomorphism is a Riesz homomorphism. Now, here we are in the lattice world, of course. So there are several observations. We, on a previous slide, we had a disjointness. So we also have disjointness preserving operators, meaning that whenever 2 elements are disjoint, then their images are disjoint as well. These operators are called disjointness preserving. And it turns out that the Riesz homomorphisms are of this type. So on one hand, they are positive, and on the other hand, they are disjointness preserving. And in lattices, the other way around is the other converse implication is also true. So every positive disjointness preserving operator is a Riesz homomorphism, is if and only if condition in lattices. This is one observation. And the second observation is that these complete Riesz homomorphisms are exactly the order continuous Riesz homomorphisms. So these 2 notions coincide. So when you deal with order continuous Riesz homomorphisms, as in the case of Kottmann operators, it's sometimes easier to know that it's a complete Riesz homomorphism, and you can use this condition that we have here. These definitions here, of course, depend on the lattice structure because we use the supremum here. But the reason last years people started to replace the supremum in a similar way as it did before with the modulus, or with the supremum was replaced by sets of upper bounds or lower bounds or by Dedekind cuts. So there are different options of introducing these Riesz homomorphisms in ordered vector spaces. And meanwhile, we have a whole theory of isomorphisms, stereomorphisms, etc. in ordered vector spaces as well. This just as a remark. Bruce will not need this, but yeah, there are many more issues there. And also these issues, when do these notions coincide with positive disjointness preserving, etc. This is not in general true for ordered spaces. So now we have all notions we need for the 3 examples, so the 3rd, the 4th, and the 5th example. And now I want to discuss a bit more this ordered vector space of the regular operators equipped with the positive cones. Yeah? So what did we already have? If X and Y are ordered vector spaces such that X is directed and Y is Archimedean, then we observed that this ordered space of regular operators equipped with the cone of positive operators is an Archimedean directed ordered vector space. And I also already mentioned that it is in general not a lattice. And it will be important that the Y, so the range space, is Dedekind complete. This is a very strong condition, but this gives very nice results about this space of operators. Let me recall what Dedekind complete means. A vector lattice is called Dedekind complete if every subset that is bounded above has a supremum. And I will present you next a theorem that is quite famous in our theory, is the Riesz-Kantorowicz theorem. And for this, I need the notion of order-bounded operators, LB. These are operators that map order-bounded sets into order-bounded set. No? A set is order-bounded if there are 2 elements where, so if they have a lower bound and an upper bound, yeah? Then a set is called order-bounded, and if such sets are mapped into such sets, then we call the operator order-bounded as well. And we have the inclusion. So the cone of positive operators is, of course, a subset of the regular operators, and regular operators are a subset of the order-bounded operators. And there appear 2 questions. First of all, when do the 2 spaces of operators coincide, the LR and the LB? And under which conditions is this a lattice? And the answer to this problem gives the famous Riesz-Kantorowicz theorem. I put it on the slide for vector lattices. Here the condition on X can be relaxed a bit to reach the composition property, but this is not important now. So the lattice version is the following. We have to look at operators between X and Y being lattices, and the range space should be Dedekind complete. And this is enough. So this condition is enough. First, that the 2 spaces of order-bounded operators and regular operators coincide. And second, that it is a vector lattice. And third, it is even a Dedekind complete lattice. So if the Y, the range space, is Dedekind complete, then the space of operators is Dedekind complete. And then the Riesz-Kantorowicz theorem gives you a list of formulas for the supremum, the infimum, the modulus, the positive part, etc. I just give the formula for the supremum here, that you get an impression how they look like. So you split, so here's for positive elements. Yeah, you split this order interval from 0 to X, and you take an element from there, and then you split you sum up over all the splittings and take the supremum. Yeah, so there are formulas like this for all the other vector lattice operations of operators. And a second nice property of the space of operators is if the Y is Dedekind complete, then these order continuities, they coincide anyway. Yeah, for positive operators. And since we were talking about the order continuous ones, the order continuous operators, let me mention that also the set of all order continuous operators was investigated in literature. So this is denoted by Ln, set of all order continuous operators in LR. And if the Y is Dedekind complete, then this set is very nice. Namely, it turns out to be a projection band. So this was an old result of Ogasawara. So that means that the space of regular operators is really split as a direct sum. So one element of the direct sum is this projection band Ln, and the other one is the disjoint complement. Disjoint in this vector lattice of operators. So maybe this gives you a bit an impression why Dedekind complete vector lattices are so important, because they will appear then in the next week's lecture when Bruce will introduce the conditional expectation operators. Yeah, that's why. Well, I mean, there are many other reasons that one wants to have Dedekind completeness, but here you see at least one issue where you can deal with these spaces of operators very nicely if the range space is Dedekind complete. So now we have done everything which you need for these examples of next week's lecture. But I want to tell you a bit, just a very brief overview of other issues, why these positive operators are so important for applications. Maybe you know the classical Perron-Frobenius theory. Now we already had these entry-wise positive matrices, which are the positive operators from our N to Rm, if we take the standard order. And the classical Perron-Frobenius theory says, okay, then the spectral properties are nice. The spectral radius is contained in the spectrum, and we find an eigenvector in the cone. And if you, if you iterate, then it gives you the long-term behavior and all these things, yeah, in applications then in systems. And behind this classical setup of Perron-Frobenius are spaces of ordered vector spaces. So if I want to do spectral theory, of course, an ordered vector space is not enough. I need a Banach space, I need a norm, yeah? And I need nice connection between the order, the partial order, and the norm. And such connections are, first, I want the cone be enclosed with respect to the norm. And second, I want that the norm is monotone. So if I have a relation between two elements in partial order, then the norms should behave similarly. And such spaces, such ordered spaces with a good norm, we call ordered Banach spaces. And then it was shown by different Russian mathematicians, so Krein, Bonsal, Karlin, and Rudman, that one can do the Perron-Frobenius theory for matrices in this general function analytic setting. So this is not about standard order in Rn. It is now about cones with appropriate norms, okay? It's now in the theory of ordered spaces. And they obtain exactly the same results if they look at positive operators, so mapping the cone into the cone. They can show exactly the same. Of course, the proofs are now long and ugly, but doesn't matter. They get the same results. The spectral radius is in the spectrum, and if it is positive and T is compact, then it is an eigenvalue with an eigenvector in the cone. So one gets the same. So this is one thing I wanted to mention, and maybe you give me for the last slide another 2 minutes that I can make some remarks on positive systems, because they appear everywhere in the applications. For example, in economy or in biology, in all these areas where you have kind of positive entities, yeah? when you start, when you want to model bacteria or whatever, you have positive entities, yeah, and the model is only good if it stays positive, or if you have goods in economy, yeah. So if your system develops, so if you start in the cone, then you want that your whole trajectory is in the cone. And now I want to show it to you in a very simple example everybody knows from basic courses in you study maths. Take a D times D matrix, take a cone in RD, and look at the linear system, or the ordinary differential equations here. You have a linear system, a d-dimensional linear system. So an initial value problem, very simple. And here, this system is called positive if your initial value is in the cone. Then the whole trajectory, the whole solution, should also be in the cone for all times, yeah, for all t. You start in the cone, you stay in the cone. These systems are called positive. And of course, we know the solution of such a system. No? When you write it out, you need a matrix exponential function, e to the at. You put in your initial condition, and then you get your solution x of t. And so when you look at this, your system 1 is positive if and only if all these operators, a to the power at for all times, are positive operators. Yeah. So that means this set of operators, this is a semigroup of operators, is a subset of the cone of positive operators. So you can characterize the positivity of such a system that comes from applications by the fact that this operator semigroup should be positive, in the sense that every operator here is a positive operator. So the same idea is done for more general settings, for the not the simple problem here, but the abstract Cauchy problem. And this leads then to the theory of C0 semigroups, of operator semigroups, yeah. And there you again can consider operator semigroups that consist of positive operators. And then you can ask, okay, which generator, so the generator here is the A, which generators lead to positive semigroups, positive operator semigroups, etc., etc. So there are many questions revolving around the setups, yeah? And it is not only about positive operator semigroups, also about disjointness preserving operator semigroups, etc., etc. It's always the question, you have a certain type of semigroup, you ask what properties does your generator have? And this abstract Cauchy problem is then used to set up a solution theory for certain types of PDEs, etc. So this is a whole big theory, but there as well is a branch of positivity in this theory of semigroups. Okay, thank you for your attention. At the end, I just list 2 standard books so the first one are the standard books on lattice theory and operators on lattices. And the last one is more towards ordered spaces. So thanks for your attention.
Thank you.
Thank you, Anke, for a very interesting talk. I have just one question. You looked at 3 types of order convergence. Now, in a Dedekind complete respace, O2 and O3 are the same. Am I? But yes. O1 is the O is not in general the same, because you have to have a very small a small index set, like a sequence or something like that, for that to agree.
Exactly. Yes.
And may I leave you to Zurab to look at the other questions? I have to go and invigilate an exam.
Okay.
Sorry about that. Thank you very much.
Could you please go to the slide where you talked about the first theorem about projections? Just wanted to ask you something about that.
Yes. No, this was the introduction, and then you want a projection slide, right? Here, yes.
Yes. Could you please remind me what is BD?
The BD is the disjoint complement I introduced here.
Right, right.
So
right.
for a set, you take all elements of the big space that are disjoint to all elements of the set.
Right.
It's the classic, disjoint complement of the set M.
So if we go back to the previous slide, what would be, maybe is it possible to like illustrate this proposition on a particular example? For instance, we pick a specific linear operator P and identify what is B and BD for it.
Yeah, if you look, for example, let's make it really simple. We look at Rn. Bruce characterized all the bands in Rn, which are subsets who are zero. So I fix some entries and let it be zero there and arbitrary on the others, right?
Right.
The disjoint complement of this set is just take the zeros on the other places.
Right.
Yes? And this splits your space into two projection bands, namely B and BD.
Yes.
Yes, and if you project on one of these bands, you have a band projection. This may be the nicest.
Right.
Of course, this is a very simple case, I know, but or you might maybe sorry, first your question, excuse me. No, you can.
So if I have a band,
yeah.
I mean, if I have a B such that X equals B plus BD,
yes,
then is it easy to show that we will get a projection out of it?
Yes, of course. Yeah, you
Right.
can then project on one of the parts. No.
So the difficult part of this proposition is that if I start with a projection.
Or a projection, yes, to split the space.
Right.
Yes.
And what is the how does one split? So how does one get the B out of the P? Maybe that's what I wanted to ask.
The range space. The range space. Take the range space of the order projection. Then you have to show that it has the right properties.
And so what is? But then I'm puzzled. So why did it take such a long time to get this proposition? What was the difficult part?
Because nobody was looking at it. This is maybe the right answer. If you go back, the disjointness in partly ordered spaces, we started 2006, and so bands were introduced in ordered spaces quite late. Yeah, and we were developed all the theory of disjointness, as Onno van Grans and other colleagues. Disjointness, solidness, ideals, and bands in ordered spaces. Then from 2006 on, and later we met Jochen, and he set then up the theory of the projection bands, and this was one of his theorems there. And I just wanted to mention a simple one here.
So one of them is the range, and the other is the kernel, right?
Yeah. Exactly. And Bruce will tell you about the multiplication in L1 spaces. When you multiply by a characteristic function, that means that you project to the band that belongs to this characteristic function. You take a characteristic function of an appropriate measurable subset and generate a band out of it. So it's the whole subs all functions that are zero outside this set. Yeah. No? And then again you see how the space splits, namely in the band that is generated by this characteristic function and this disjoint complement, which has the other, how to say,
Okay, if I can ask, yeah, thank you. But if I can maybe rephrase my question. So let's say instead of BD, we say explicitly in condition 2, we explicitly say that we take kernel and we take image. And then isn't the fact that we can decompose X as a sum of the kernel and the image, isn't that like straightforward?
Now the thing here is that they are disjoint.
I see. Okay.
It's not
So,
only a
okay.
direct sum, it's a disjoint direct.
Okay, so it's the fact that the kernel and the image are disjoint that's kind of
Yeah.
what plays the role. Okay, thank you.
Yes, yes.
I'm not sure if there are any other questions. Maybe we can wait for a minute or two. Otherwise, I'll pass it back to Francesco.
Yeah, sorry. Thank you very much, Anke, for the nice lecture, and thank you very much to Bruce and Zurab for helping out during and at the end of the talk. Yeah. Just maybe a reminder to the participants that the fourth lecture in this series will be not next Wednesday because it's a public holiday, but next Thursday at the same time and using the same link. We will send out a reminder in due course via through our mailing list. Yeah. So please don't forget that there is one more installment of this course. Yeah. So thank you very much, Anke. We were looking forward to see you in action again next week. Thank you very much.
It will be Bruce next week.
It's Bruce next week. Okay, sorry. So then thank you very much for the intermezzo.
Okay, it was just an intermezzo, yes.
Thank you very much. Thank you very much. Then a good afternoon to everyone and a good public holiday next Wednesday. And on Thursday, we will be back here. Yeah. Thank you very much, Anke. Thank you. And thank you, Zurab, as well. Thank you very much.
Thank you very much.
Bye. Bye-bye.
Bye.
Cheers.
Bye.
Bye-bye. Bye. Cheers.